we're trying to figure out how to recombine or how to use the DR plan that we create in order to minimize the algebraic complexity of finding a realization of a geometric constraint system. And we have primarily talked about distance constraint systems. And we gave a combinatorial description of how to optimize the algebraic complexity for a class of parameterizations that we described, rational parameterizations that allow us to put together at every point in the node in the DR plan the solutions of the subsystems, the child subsystems, which are rigid, which correspond to rigid subsystems, and have zero-dimensional solution set, how to put them together to create, to solve another system at the parent, and thereby find the solutions to the parent system. So the understanding is that you sort of pick one solution of each subsystem and substitute it into the system corresponding to the parent and solve it. So we went through that process, and we defined this idea of an overlap graph, which is a weighted object that's based on, how the child subsystems are put together to create the parent system. And we, after creating the overlap graph, we found a covering set that gave a sort of a minimal spanning tree according to those weights, where the weights represent the number of variables in the final system that you would be solving, and then also optimize after, once the spanning tree, the best covering set that gives the optimal spanning tree is found, then we find the root, decide where to place the root of the spanning tree, which also decides the degree of the system. So that way we minimize the number of variables and the degree of the system that's solved at the given node of the DR plan, given the solutions for the children. And we gave some examples, 3 or 4 examples of systems, platforms, kind of systems that were solved, Stewart platform type of systems. And, using this method, and here's an example of the different solutions we got for one of these platforms. Okay, so then it was pointed out that there's another issue that comes up when you're trying to solve these systems in the way that we describe, which involves having some incidence constraints in the final system. So going back, for example, to the example that we talked about here, if we took the covering set consisting of C1, C2, C3, and C4, in this particular case, there are no incidences. There are just eventually, you parameterize this system as using its rotation about this axis, and this one using its rotation about this axis, and this one about its rotation about this axis. And so those are your variables, and then eventually all you have is the distance constraint. So there are no incidence constraints involved here. But if you remember the original way that we had, the unoptimized way, and it could well be that the optimized way also has that feature. The unoptimized way was to have C1, C2, C3 as the covering set. And then in that case, you would parameterize C3 as a quaternion, 3-dimensional 3 DOF rotation about the point B, and then you would parameterize C2 by a 3-dimensional rotation around the point A after choosing C1 as the home cluster, and then you would have one incidence constraint here with C, and then saying that C in this system is the same as C in that one, in the solution of this system is the same as the C here, so that would be 3 equations here. And then you would have the 3 distance equations. In a similar fashion, you could well imagine a situation where the incidence constraint is not just at a point, but in fact at a pair of points. So we will look at a pair of points that are in two different clusters, that are shared by two different clusters. So the example here is one of those. So this is talking about the three clusters C1, C2, C3, which share essentially pairs of points. So if you try to use the method that we had, you know, the overlap graph and the covering set and so forth, you would pick the C1 and C2, let's say, and say that, okay, so we can parameter and say C1 is the home cluster, and then you can home subsystem. So again, this is the picture, just to take a step back, the overall picture is the same. C is the entire thing, and C1, C2, C3 are the children. We're trying to place, having solutions for C1, C2, C3, we're trying to find a solution to the clusters, the overall system C. And here, if we choose C1 as the home cluster, you could potentially parameterize C2 by rotation about this point, so that's okay. But then you have these two incidences. So C3, for example, would be then incident upon C2. You could also parameterize C3 by rotation across this, but then you have the incidence on this edge between C3 and C2, right? So what we're looking at now is, for a moment, let's forget about this overlap graph thing. And we'll put that together. There was another separate paper that put together this overlap graph-based optimization here, which has underlying it the matroid that corresponds to the spanning tree. So that's the usual graphic matroid, with this other matroid that comes up in resolving these incidences. So for the moment, let's just assume that we're looking at the entire system of incidences here between C1, C2, C3. So C1 and C2 are incidents on this edge V2, V4. C1, C2 are incident on this edge V4, V3, and so forth, right? So, so the question is, how many of these incidences are independent? So I have to be careful to tell you why this type of independence is actually interesting. So numerically speaking, you know, when you have the solutions to C1 and the solution to C2, and you have a placement of the vertex V3 and V4 in C1, and you also have a placement of the vertex V3 and V4 in C2, and let's say this edge actually existed in the graph, you would expect, if these are proper solutions, that the distance between V3 and V4 in C1 and the distance between V3 and V4 in C2 would be exactly the same. But that's never the case because you're doing this numerically. So you end up with the distance, even though it was asserted as a constraint in C1, and this distance was asserted as a constraint in C2, the placement of V3 and V4 in C1 is usually slightly different from the placement of V3 and V4 in C2. And you would realize that, in fact, if you're going to constrain these two with the same distance between them, you would have maybe three equations saying that the position of V3 in C1, by the way, this is three-dimensional. Everything that we've seen recently is three-dimensional. This continues to be 3 dimensions. So, so the position of V3 in C1, just three coordinates, equate them to the position of V3 in C2. But then, because this distance is the same between them, in fact, you can equate with independently only two of the coordinates of V4 in C1 with the two of the coordinates of V4 in C2. So just by looking at the single constraint, you would say, okay, I can only equate two of them. And then do the same thing here. And if you think about it, you know, once you have equated these, then after that, you only have, you know, one that you can equate between these two and one here. And so this is basically showing different ways in which you could try to resolve this type of dependence by using an independent system of constraints. I mean, independent system of incidence constraints of this type. But you know, there are many ways you could try to do it, and all of the ways are somehow local in the sense that I've shown here. I mean, that are local in the sense that I look at each constraint separately. But in fact, these constraints, these incidence constraints, form a sort of a global system where dependencies could sort of be transmitted, across the clusters. So that's sort of the classical situation where you might expect that there is some type of matroid there. So this is another example. These are all in that. I mean, I put the references somewhere on these slides. You should be able to find them.
Meera, could I ask a question?
Yeah.
Could we go back to that slide that you just had with the this one? Yeah. Yes, thanks. Yeah. So we're talking about the number of independent equations here.
Yeah.
But how do you, in what order does one solve them, right? Because we solved I was under the impression that we solved each of the child systems first.
Yeah, those are already solved. Yeah.
Then we patch them together.
Exactly. And the question is, how do you, I mean, what is the system of incidences you use to patch them together?
I see. So it's really just figuring out rotations and translations in order to make the patching, and those rotations and translations have dependence constraints upon them. Okay, now I understand. Perfect.
Yeah. So the rotations and translations are just like what we defined here. I mean, these type of things. Yeah. So I mean, I've simplified it even further compared to this for the moment. Yeah. So I mean, here I'm just saying, let's say that C1 is, and there's some rotation of C2 and rotation and translation of C2 and rotation of the translation of C3 that I need to figure out that satisfies these constraints. Yeah.
Is there an advantage to solving to patching the constraints in one order rather than another? Does it make sense?
Yes, that's what this previous section was about.
That's that ordering of the overlap.
Exactly.
Graph. Okay.
Right. Perfect. That overlap graph and the covering set and the spanning tree and the ordering, partial ordering is given by where you put the root of that spanning tree.
Okay, now I'm following. Okay, good.
Okay. But now for the moment, I'm asking you to forget what I just said, because forget the just immediate previous lecture and just think about these separate, just as though I'm doing it the dumb way without doing that. Okay. So all I'm doing is picking C1 as a home cluster and figuring out the translations and rotations of C2 and translation of rotation of C3 and have this one big system to try to solve it. Yeah. And then later we will put the two, there is an underlying matroid here. There was an underlying matroid that gave you the spanning tree in the previous approach. And then I will try to put those two together. Yeah. So at least indicate it. I don't know if I'll have time today to go through that. Okay. So here's another example, of various different ways you can do this. The slides are available. You can go have. So this one actually shows a bad one, and that these two are good choices, independent choices. Okay. So now I just want to recall that what we're looking at is, we're starting out with something that someone promises is an independent system, right? So what they gave you was a system of distance constraints that was independent. And then you formed the DR plan, as we showed in the previous slides. If it is not independent, if it was actually dependent, finding an optimal DR plan is actually NP hard. But given that it's independent, you actually have a way to find the optimal DR plan, which means optimal recursive decomposition into maximal rigid subgraphs in polynomial time. So that's the assumption that we still go with, is that the overall system is independent, and therefore we have this complete canonical DR plan and all of those things that we defined, with that same properties, that every parent is split up into the complete set of its maximal rigid subsystems, and if there any pairwise intersection between them is non-trivial, then it's sufficient to take exactly 2 of them. And if otherwise, all of them are there if their pairwise intersection is trivial. And we showed that this was a well-defined, you can always divide into only one of these 2 cases, and that the union of the children was the parent and all this. So all the previous lectures that all the previous stuff that we did, we're going to use this property of this canonical DR plan here as well. And the fact that we're starting out with an independent system. So given that we have something independent and we have this canonical DR plan, we can make certain assumptions about degrees of freedom just through counting, right? So counting works because we know it's independent and we know we have these properties. So we can define something called the adjusted degree of freedom, just simply a kind of a inclusion exclusion count of the number, the degrees of freedom that you would expect this system, this recombination system to have. So if you have the standard decomposition, which is just what we called canonical decomposition of a constraint in this manner, so into its maximal subgraphs, maximal rigid subgraphs, then the expression for the adjusted DOF uses this inclusion exclusion, which is simple. It says that for every subset, you take the subset of the set of children. So C is the parent. You can think of, so basically T is a subset of its children. So and you're looking at every possible subset of that, and you're simply taking this degrees of freedom of the intersection minus the degree of freedom of the shared part, right? So, and then this sort of, becomes, you can simplify it by simply taking 6 times the number of actual clusters or subsystems or children, if you will, plus 5 times the number of shared parts between them, and 3 times the number, shared edges and shared vertices, and other portions here. So SV, I should have gone back to the paper. The paper is, where is the paper? I should have, okay. When I make that, when I send you, put the slides, I'll ensure that all the things are defined. I thought they were all defined, but apparently not. Okay, so let me quickly go to the paper. Okay, so this is not it. Go back. Shoot. Okay, here, I think this might be it. Yeah, there we go. Okay, this should be it. Yeah, this should work. Yeah, I was trying to avoid this scrolling through this thing, but I think I forgot to pull out some of the definitions. So that is no good. Okay. I'm in the middle of it. Where is the definition of this? Defined as above. Okay, here. This was the original one. Okay. I'm sorry about this. Okay, so here is the definition. Okay, good. So here it is. I have to change. Okay, stop share. And okay, so there we go. Share. So here's the definitions that I forgot to bring there. So can you see the screen?
Yeah, it's fine.
Okay.
Yes.
So I'll make it a little bit bigger. Get rid of this. Okay. So so we have the C, which is the recombination, the system, particular node of the DR plan that you're looking at. And D is a standard collection, which is just because it's a standard decomposition, just a canonical decomposition. So you have rigid subsystems, and you can, without loss, assume there are a whole bunch of them. So not just two. So without loss, you can assume that their intersection is non-trivial, is trivial, because if they were non-trivial, it's really easy. They share more than in 3D, 3 vertices, and putting them together once you have the solutions of each of them is trivial. So VD and ED are the sets of objects of C that are shared by more than one child. So you basically have a collection of subsets of the set of objects, which vertices, where CI contains all the vertices in VD that belong to one cluster. And for each V, you have, and each vertex and each edge, the set SV and SE are those that are those clusters that contain the vertex or that particular edge. So in other words, if there's a common shared vertex or edge, then there's a bunch of clusters that contain that vertex or that edge, and that's the set SV and SE. So the pair CD is a canonical decomposition. So this is simply just defining what we already know, just seen a few times. We can assume that the intersections are trivial, and because if it's non-trivial, it's extremely easy, the recombination system. And then for every triple of points, we know that the intersection of the set of clusters that share each one of those points is at most 1. Also, that follows from the fact that that the whole thing is independent. So, and we also know for every pair, the set of clusters that share that pair is less than or equal to 1. So the intersection between the set of clusters that share one of those edges and the other edge is 1. All of these just simply follows from the fact that their common intersection is less than or equal to 2, right? It's a trivial, the standard decomposition case that we're looking at, or canonical decomposition case that we're looking at, is you have a cluster C and the pairwise intersections of all of their children are all trivial. Okay, so so those are the notations, and from that we can define the number of degrees of freedom, because everything is independent and we know that it's a canonical decomposition. We can define this adjusted degrees of freedom, which is if given the cluster C, D of its children, and T is any subset of it, you can look at every subset of it of size greater than or equal to 1, and you can take the degrees of freedom of the intersection minus the degrees of freedom of, so okay, X is defined here. XT is the set of non-shared external constraints relating the objects in these clusters. So for example, we had those additional degrees of, additional distance constraints or additional incidence constraints, which are not shared, which involve objects that are not shared between any pair of clusters, those are those XTs. So if you subtract those degrees of freedom that are removed by those constraints, then you basically have this. Okay, so none of this is true if you didn't start out with something that was independent. And so that's a big assumption. And we know that it is a big assumption because we know, for example, that finding an optimal DR plan in the case of dependent systems, we had an example right in the beginning, is NP hard, whereas we have a polynomial time algorithm in finding an optimal DR plan. Essentially, we proved that the canonical DR plan is optimal, and finding the canonical DR plan is polynomial time. And as a result of which, we have a polynomial time algorithm if the original system was independent. So now I want to stop sharing this and go back to the other screen. So this one. Okay, so now we know the definitions of all of these things, and we can take that original definition of the adjusted degree of freedom, which is just a simple inclusion exclusion, and massage it into this form. It's a little bit easier. So instead of having this thing, which was the original definition, we can actually get a simpler definition. Easier to compute because you don't have all the possible subsets and so on and so forth. So this would be like an exponentially sized thing if you did the summations, but this makes it much simpler. It just sums over the edges in the that are shared, the vertices that are shared, the constraints that are between pairs that are not shared, and all of these degrees of freedom. So this is for 3 dimensions and this is for 2 dimensions. It's not hard to see that this the first expression here simply becomes these expressions. So so there's this other residual DOF or whatever that is of use, which I will simply put here. So you have given a subset of children, given the set of all children and any given subset of it, SB, remember, is the set of all clusters in D that share a particular vertex. And this is the set of all edges in D that share a particular vertex. And then this particular quantity is defined, this RDOF, and this is ED is the common shared edges. In the 2D case, they don't exist. The trivial intersections are of size 1. So you only have this. Okay, so these are numbers, sort of quantities to keep in mind. So, and another notation to keep in mind before we talk about this matroid is this triple VCICJL. What this is saying is that V in the shared point at which the incidence is asserted, Ci and Cj are the sharing clusters in D, and L 1 less than or equal to L less than 3 denotes the particular coordinate x, y, or z of the point V, which is equated by that incidence constraint. So an incidence constraint is represented by the vertex at which the incidence is being asserted, V in the set SV, and Ci and Cj. So in other words, the shared vertex and Ci and Cj are the particular sharing clusters that I'm referring to. And L is the particular coordinate of that vertex, coordinates of that vertex that are being asserted as being equal. So in the case of 2D systems, L is going to be less than or equal to 2. Okay. Now, so we define this well-formed set of incidences in 3 ways. So first of all, there is no local cycle of incidences. And so in other words, you don't have the situation that for a given single vertex. Remember this vertex, notice that all of these vertices are the same vertex. So, and they're all being, they're shared by this whole bunch of clusters, and we are asserting an equality at that vertex between the first two clusters, the second one and the third, and so on and so forth. And then you don't have like the k being ik being equal to I1. Because if you do that, you have a cycle of incidences, which numerically will give you problems. Okay, so you don't want that. So there is no local cycle. So then we're saying that for any subset of clusters, let I dt denote those incidences, these incidences for which Ci and Cj are in this subset T. So for any T, we want to make sure that the number of incidences that we assert is going to be less than or equal to this difference, this what we call the residual DOF of dt. So this is a kind of a Maxwell condition. So it's saying that this number of incidences that we assert has to be smaller than or equal to this number that that would correspond to an independent set of incidences. And then the total number of incidences should be actually equal to the total number of residual DOFs that you expect in an independent system. Okay, so these are the definitions. This is how we define a well-formed system of incidences. And once you have this, you won't have any of the numerical issues that we talked about. So this is motivated, this definition is motivated by the practical difficulty of solving this system of incidences if you have numerical issues. Now what we show is that having defined it this way, that we now have this notion of well-formedness turns out to be independence of something in a certain matroid. Okay, so what is that matroid? So we're going to define for a standard decomposition an undirected graph. So here's your standard decomposition set of clusters, the total set of vertices, so total set of edges. And we're defining this graph where the set of vertices are all the vertices, the set of edges are going to be PE union LE. And that just means that you're taking every vertex in the shared, in all of them, and you're simply taking all pairs that belong in V. So what we call these the point seam edges, and these are called the line seam edges. So it describes it here. Okay, so essentially what we have is that the set of vertices, the edges are of two types. The first is called the point seam edges that connect every pair of vertices UV in the set, forming a complete graph. So in other words, what you have is that if you have a particular vertex appearing in multiple clusters, you're just going to make a complete graph that takes all the different copies of them, right? So notice that here you're simply taking a simple union of all the copies of the vertices that are present. So in other words, if a single vertex is present in more than one cluster, you'll simply have that many copies of it. So this is saying that between the copies of the same vertex, I'm putting a complete graph, right? So those are called the point seam edges. And then the line seam edges are essentially if you have a particular edge that belongs in two clusters, then you make two copies of that edge. So in how many ever clusters it belongs to, in how many ever elements of D it belongs to, you make that many copies. And so it consists of SE copies. SE, remember, is the set of all clusters that share a given vertex, edge E, copies of every edge. And for each edge and each cluster that shares, we create a copy of, so we create a copy of that edge. So you have a copy of all the common vertices, one copy each for each of the clusters, and one copy each of the edges, shared edges for each of the clusters that contains it. So that's essentially what we call the seam graph. It should be clear. And here's an example. Here was our original. So if you have this system, the original system that we had here, this one here. So you have V3, V4. So this guy is shared by 3 clusters. So it'll have 3 copies, and with a click, which is just a triangle here. This guy is shared by 2, so it'll have 2 copies. This will have 2 copies. This will have 2 copies. And the 2 copies here will be connected by an edge, because that's the click. And here click, click. Plus you'll have, this guy will have 2 copies of this edge, 2 copies of this edge, and 2 copies of this edge. And that's exactly what we have drawn here. So essentially you've got the click in the middle, because this vertex is shared by 3. This is shared by 2, shared by 2, shared by 2, and then 2 copies of the shared edge, 2 copies of the shared edge. So this is what we call the seam graph. So now you know, this would be a seam path, what we call a seam path. And the seam path is not some arbitrary path in the graph. It has to have this pairing. So in other words, whenever an edge corresponding to one of these, what we call the line seam edges, then its partner, one of its partners, should also appear in the path. And it should be separated by one of the point seam edges. So it could be that there is no point seam edge, like in this case, that separates them. I mean, that separates 2 line seam edges. But if you look at 2 partner line seam edges, they'll be separated by. So that's like a seam path, and this is a seam cycle. So these are all allowed paths and cycles. That's why we give them the name seam. And this would be a seam tree. It's another seam tree. Okay, so and these would all, the seam trees, complete, whatever, spanning trees. I think we don't call it spanning, but it's a connected tree that contains all the vertices and all the vertices of the seam graph, and has this seam path structure. Everything in it is a seam path. So those are called, so those are all defined here. A seam path is defined between a connecting pair of vertices. Connecting a pair of vertices in the same set of the seam graph GD. We denote a path as a sequence of consecutively incidence edges. The path assigns each of its edges a direction. Seam path between U and V is a simple path that is the concatenation of simple path segments. And so U and V are the first and last vertices, and the segments are of 2 types. Those are the H segments and the G segments. The H segments could be empty and consist only of point seam edges. And the G segment, each G 2J plus 1 is a single edge in the line seam edges, and it has a unique partner edge, G2L plus 1, such that both edges belong to the same, belong to the same set. So in other words, all of those line seam edges correspond to the same edge, E, in the original graph. So then they appear. So that's the definition here. So that's how we define these seam graphs. And then you can talk about spanning subgraphs, as induced subgraphs, then and they should be line inclusive, which means they have they include all of the line seam edges in this. And when the context is clear, we simply identify these subgraphs with their set of point seam edges. And then the seam forest is a seam subgraph that does not contain any seam cycles, and seam subgraph is seam connected if it contains a seam path. And remember, we have to keep saying seam everywhere because it's not an ordinary path. It has this condition that you have the partner edges there, and so forth. So seam tree is a seam forest that's also connected, and then so etc. So the rest of the definitions are what you would expect. The only weirdness is this idea of the 2 things that one is that, you know, the seam path has this idea of partner edges being present, and when we say spanning, we mean that all the line seam edges should also be present. Okay. So so in this case, we have different so we have the situation of bad and good choices of incidences. So you will see here that seam cycles corresponding to the bad choice of incidences. So this was this example. If you look at this example, it's hard to do during a lecture because it requires some staring at it, but you'll see that this is a bad example. It doesn't satisfy the well-formedness criterion. that for numerical stability, and these two are good. And now we want to show that these two good ones correspond to actual seam trees, and this one does not. Okay, so that's what this is doing. So not this. This one is doing for that example. It's sort of showing here's the seam graph. Look at the seam graph here. And isn't it missing something? No, I think that was a different example. Let's see. Yeah, this was a different example. Okay, so this is we'll come to another bigger example later. Okay, so this one has, yeah, so this is the seam graph, and you'll see that some of these are not good, and some of these are good. So basically, it says that these two are seam trees that correspond to the well-formed choices of incidences. So it follows the exact same picture that we have here. So if you go back to this picture, the top left is the seam graph. We draw the seam graph for it. The top right is has the seam cycles, which shouldn't be there, and the bottom two are seam trees, which are good. So essentially, you see the bad stuff happening, and this is good stuff. Okay, that requires staring at that example for a little bit, so I'll leave that for later. So essentially,
can I ask a question?
Yeah.
So when we have the good or the well-formed seam paths,
yeah,
you mentioned that corresponds to good numerical stability properties for the solutions or for the algorithms?
Yeah.
How does that work?
Yeah, that so that was sort of what I was explaining in the beginning. So if you have a solution to this cluster, or you have all the placements of all the vertices and everything in this cluster, and you have the placement of all the vertices in this cluster and so forth, then when you try to find the rotation and translation of C2 and C3 so that they fit together to satisfy this condition, this incidence here, what you would do is
they're just off a little bit.
They're off a little bit. So now when you try to say that, V4 is common between C1 and C2, and you say, that the three coordinates of V4 in C1 and the three coordinates of V4 and C2 are the same. And then you have another three that says the three coordinates of V3 and the three coordinates of V3 and C2 are the same. Then what happens is that's over constrained, because in fact, they're slightly off, right? So the distance between them here and the distance between them here are different from each other. So that 6 constraints that you assert there are over constrained. They're inconsistently over constrained. So what you should do is just say, well, I'm going to assume that this distance is the same between them. So in fact, the number of degrees of freedom that I have at my disposal is 5. So the common thing here is 3 degrees of freedom that I can assert here, and only 2 over here, or vice versa. So 3 over here and 2 over here, something like that.
Right.
But it's not just locally for one edge. In fact, all of these interact across all of these. That's what I'm trying to say.
Right. And that's what the seam graph allows you to do, exactly, is to keep track of how they interact and to kind of avoid using extra constraints that would now make your system unsolvable.
Exactly.
That's the sense in which the numerical instability is there. It's not like a Newton's method kind of thing that it's diverging. It's rather that we're imposing an extra constraint that's not satisfied.
Right.
Okay.
And that's exactly what we're saying here with this with this condition. We're trying to sort out how many constraints should we be asserting for any subsystem.
Yes.
Right. So that it's that we can solve it. And that's what this is. And that's how we arrive at this definition of well-formed system.
Okay, so I have one more question, which relates to these incidence theorems that I spoke about yesterday in the seminar. There are sometimes constraints that you don't put
I know.
into the system explicitly, but
Yeah.
but they somehow are there, right?
That's true. We are
and-
assuming some genericity, like we are assuming, like, for example, things like 3 points don't lie on a line, and
Perfect.
all
Okay.
that kind of stuff doesn't happen.
Understood.
Right? So yeah. So these are just distance constraint systems. We happen to have already solved portions of them, and we're trying to put them together. And when we do that, we're asserting some incidence constraints. Yeah.
I see. I see. So
And
these are what I would call expected degrees of freedom.
yes,
They
these are
may
expected.
turn out to be over estimates slightly in special position. If your points were in special position, the degrees of freedom can drop somehow.
That's right. And not only can they drop, I mean, in fact, if even in all ordinary bar and joint rigidity, if I had not previously assumed that the whole thing is independent, in fact, we would have hidden over constraints here too, like in the 2 banana case or all of that, right? So there are no dependent constraints. That's what we're assuming right in the beginning. And that's an assumption that we've had now for 3 or 4 lectures, because we would not have been able to get this polynomial time algorithm for the canonical DR plan otherwise, because we have actually shown that in the general case, getting an optimal DR plan is NP hard.
Right. Okay.
Okay. So that's an assumption that we have made throughout in the last several lectures. But even then, there are these intricacies that need to be sorted out. Yeah.
Yeah. Yeah, no, it's understood. Okay.
Okay. So here, okay, so we defined, so here's the main consequence here. Did I show this picture? Yes, I already showed this picture. Okay. So here's the main theorem. So basically a seam tree in a seam graph can be found using a greedy algorithm because it happens to be a matroid. Okay. Even though it has this weird seam property, it's not quite the graphic matroid. It's got special paths and special notion of connected and special type of tree, but it turns out to be a matroid. So, and because of that, we can find the seam tree using a greedy algorithm, just like you would a normal tree. And the other thing is that, where's the corollary? Okay, well, before the corollary, we have an example. So here's the another sort of slightly more complicated example. And you'll notice here that this cluster has just shares one vertex. So it's sort of off here by itself as a as a separate pair of point seam vertices with point seam edge here. And the rest of it is like this. So I have this example to say that, it's not the maximal connected spanning subgraph may not be a tree. So we may have to have something separate here. That's showing that. But it's also showing this interesting seam graph for this system here. And the corresponding, so here's a seam graph, and you can find this is an example of a seam, a spanning seam subgraph. And so this part of it is the seam tree, and then you've got this thing. And so essentially the other theorem that says is that, if we ensure that we get a seam tree, then we get the right number of equations that we wanted. So in other words, we define this notion of a well-formed system of incidences by saying it's got the right number of equations. It should have the right number of equations. And then we separately define the seam graph and the seam tree for it. And now we're saying that, in fact, if you use the seam tree, then you get what we want. So in other words, the rank of the underlying seam forest matroid turns out to be exactly the number of equations that we want for each. So we get a well-formed system of incidences. That's what this is saying. Okay, so yeah, so corollary says there's a well-formed set of incidences for a standard decomposition. Remember, standard is just canonical for a 3D constraint graph. And then this is saying that because there's an underlying matroid, we can quickly find the seam forest or the spanning seam forest or seam tree for each connected component of the seam graph in fairly fast. And so we can get this system into a numerically stable form in polynomial time. So essentially that's what this is. This is simply showing the corresponding set of incidences that that particular seam forest that we found, spanning seam forest that we found, would assert. And there's just no way you would. This is just to illustrate that if you eyeballed it and tried to do this, you wouldn't know how to do this. Okay. So, and I have to say that this was an example of a problem that arose really because I write mathematical software, my group writes mathematical software, and we had to scratch our heads for a long time because we'd end up with something that should be solvable, but we wouldn't be able to solve. Then we would, because the thing would come back and say, so sorry, this distance that you found for C2 and this distance that you found for C1, although both it's a single edge that's present in both of them, are different from each other. So you can't solve the system of the whole thing for C. And then we would, eyeball it and try to sort out these dependencies in some way, but then they'll turn out to be all wrong. So, then we said, oh, we got to pick this set of incidences that we assert in a very careful way here. And then that came to the formalization of the problem of this well-formed system of incidences, and then came to the formalization of this idea of this underlying graph and matroid and so forth. So this is exactly the type of problem that I find really interesting, that, I didn't cook it up as a mathematician. I think of myself as both a mathematician and a sort of an applied person, but it actually arose in an applied context. And I had to, find the sort of mathematics underneath it. And it turned out to be very interesting. The last bit, which is, okay, you said we had this other way of optimizing. So you can think of it as the first thing that we talked about was optimizing the algebraic complexity using a combinatorial approach with the spanning subgraphs of this overlap graph. And the second part was just, in fact, maybe I should have done the second part before the first. The second part was just ensuring that we have some kind of a well-formed system that we're solving. So there's an optimization and there's well-formedness. And both have different matroids underneath. And the question was, how do these matroids interact, right? So in other words, if I went ahead and did this optimization, ignoring the well-formedness completely. So here, if I did this optimization, ignoring the well-formedness, is it possible that I end up with something that's not well-formed? Or conversely, if I did the well-formedness first, and there are many possible well-formed choices, how do I, then after that, I have to go and do the optimization among the well-formed choices. Will this overlap graph approach, will that even work? So that was the question. So we wrote another paper that sort of said that, in fact, you can do them one after the other and you don't lose anything. So, and in neither in terms of complexity or in terms of something going wrong. So unfortunately, I don't have time to do that, but, and next week, Sean is starting, but we have a few grace things, we'll tie up some loose ends at the very end or whenever we have a little bit of time in between, and then I can do it then. Any other questions? So the new set of slides are on, I've already put the copy on the Piazza site. I will ensure that the place where I had forgotten to put the definitions, I'll add a new slide so that the definitions are there. And somewhere here, and then update the slides. Okay, let's stop share.
Thanks, Meera. This is really cool stuff. I mean, it's really excellent when you can see the algorithm kind of coming together, bit by bit, and seeing the obstacles in place that you had to solve. It's really a nice way to learn this material. So thank you.
Yeah. It's a nice way to learn the material. Yeah, I agree. Okay.
Maybe a little bit more frustrating if on your end, in the sense that you had to go through the learning of it without knowing that there was a solution at the end.
Absolutely. I mean, it doesn't happen often that you have such a nice solution at the end, it's usually messy, some mess, so in this case, I have to say, from start to finish, we started this frontier geometric constraint solver for 3D, which is open source. We started it around 2001 or so. And this paper, as you can tell, came out, this well-formed paper came out in 2006. And the optimal parameterization paper came out in 2010. Now, they didn't all take that long. Let's say it took about 5 years. And there's a student who actually struggled through it, who was writing the software. So who actually saw the whole thing unfold, So I think that was a very good experience.
That's very cool.
So I'll stop recording.